Okay, let's get it started. Hi, everyone. I'm Mohammed. I'm a senior researcher and lecturer with Professor Mutlu since 2021. I'm also one of the instructors in this course. Unfortunately, today, Professor Mutlu couldn't attend and give lecture since he lost his voice yesterday. I think folks that they attended seminar, they realize it. But he will be online and hopefully can also answer or contribute to the lecture if needed. So we're gonna continue today with the part that we left off yesterday and how like the memory system challenges and opportunities. And we're gonna see a lot of examples today how we need to basically, work through the entire stack from the software to the hardware in order to make intelligent architectures. And after the first part of this lecture, which I think it's gonna take most of today's lecture time, we're gonna also have a short part lecture in about course logistics and grading and those boarding stuff. So yeah, are there any questions from yesterday? Okay, good. Let's get it started then. So basically, we want to see why is memory so important, and especially is more important today. And we discussed about this stuff yesterday, just about to jog your memory. Like memory is quite important, and we look into it from the performance perspective, from the energy perspective, scaling and robustness that covers reliability, security, and safety, as well as trends and challenges, opportunities in main memory. And we discussed about the energy consumption, and that's basically a lot of energy is consumed on memory system, as well as also the off-chip main memory, which that cause a lot of energy inefficiency in today's systems. And this is a slide that we also covered yesterday, that we spend much more energy, like orders of magnitude higher energy consumption, when we want to bring data from the main memory to the system, to the processor, in order to do some operations, like arithmetic operations. And this is actually also we observe in this plot. And we also discuss about it that if we consider the overhead of bringing data from the storage to the main memory, and then from the main memory to caches and also the processor, the overhead is going to be even higher. This is also data that we basically presented yesterday on one of the paper. That basically around 63% of total system energy is spent on data movement for basically mobile workloads. And also we observed that in large ML models on edge devices, we have even higher, like around larger than 90% of total system energy is consumed on memory, on data movement. And these are the also slide that you are already aware of that. So yeah, so we discussed about the need, it is a paradigm shift that we need to enable computation with minimal data movement, and we need to provide computation where it makes sense, where data resides. And that makes the computing architectures more data-centric. And this is also the picture that we first showed, that that system has like some processor system on chip, let's say, that has a lot of SRAM, and then we have a lot of DRAM, and then we have a lot of storage. So when we want to make things better, like data-centric architectures, we need to basically try to provide computation in all over the system. And that can distribute the computation all over the chip or over the board. So for example, we have sensors, so why not providing processing near sensors? So in many cases, so when sensors capture data, we need to do some algorithm like sensor fusion. So why not having computation close to sensor to those computation? And also we have storage, so why not making storage capable of doing computation, as well as DRAM and also SRAM. So that can actually make things much better and much more efficient. This is the slide that I think we left off yesterday. So basically, we want to have processing inside memory or storage. And this can be actually one example of how we can envision this system. So there's a processor with cache and also memory storage, and you have some applications like database, graphs, and media, and you can actually store basically application data as well as important, like the computation of those applications inside the memory and storage. And the processor can just query like some information to the memory or storage, and then we do internally computation inside the memory, and then we just send the result to the CPU. So it is completely different from the CPU-centric computation, which is you need to move data from memory storage to the processor to make decisions. So here we are trying to do all the computation inside the memory or the storage, and then we just send some results to the processor. And that can heavily reduce data movement. So, but of course, there has been, there are many questions that, like, how do we design the compute-capable memory and controllers, how we design processors and communication units, software and hardware interfaces, system software, compilers, languages, and as well as algorithms and theoretical foundations. So this is actually also something that I want to focus on a little bit now. Like the idea of the theory of, evaluating the complexity of the algorithms is much more processor-centric. It's about how many instructions we can do. I mean, we should do in order to, complete an algorithm. But so we do believe that in theoretical foundation also needs to be revisited and consider data movement as one of the important part of that. And at some point, they can be actually new theoretical foundations that consider data-centric computing paradigm. And all this can actually be achieved by looking through the entire stack from the problem to the electrons. I mean, not probably electrons, but at least from the algorithm to the devices. So if you want to learn more about this, basically processing memory, a modern primer on processing memory, I would suggest that you check this book chapter. We also, we're gonna release the new version of this book chapter also soon, so stay tuned. But this is also, I think, one of the earliest version of this book chapter. So, like also we know that main memory is also, as we discussed, like the energy bottleneck, and also DRAM technology scaling is also ending. So there's also this ITRS projects that DRAM will not scale easily below X nanometer, and scaling has provided many benefits. So far, like higher density, lower cost, and lower energy. But we have difficulties in scaling and even more, and that creates a lot of robustness problems. If you want to learn more about these scaling challenges, I would refer you to this paper from Professor Mutlu. So yeah, but let's basically learn a little bit more about why DRAM scaling is a problem. So DRAM stores charge in a capacitor, like the charge-based memory. So you need to store charge in capacitor, and you need basically large and powerful access transistor to make sure that basically you have low leakage and can provide high retention time. So whenever you charge this capacitor, after some time, if you don't access your DRAM cell, the charge is going to be leaked, and at some point you cannot really read your data properly. So that access transistor needs to be basically worked on to make sure that we have good retention time. And that actually basically brings us to this problem of scaling. So, building this capacitor is not easy. And also that transistor cannot be, too small, because if it's too small, then retention time is actually so low. And when retention time is so low, you need to refresh your DRAM more and more. And by refreshing your DRAMs more and more, then you will consume a lot of energy. And that brings you to this loop that makes everything worse and worse. So yeah, so essentially DRAM capacity, cost, and energy power, they are hard to scale. This is also, the quality is not really good, but yeah, it's like a picture of die photo. I think we have also a better one here, I guess, yeah. So these are like the capacitors in the DRAM die. And this is the bit line, and also you can see the access transistor here. But yeah, so in the end, it's not easy to build DRAM. So, but DRAM is not the only memory that has that problem. Like also flash memory is also is a floating gate charge. So we're gonna also learn about flash memory more in this course, but very briefly, in flash memory, we also have a floating gate. it's a transistor that there is a floating gate that you need to basically provide positive charge, and then you can trap some electrons into this floating gate. And by doing that, you're gonna basically increase the threshold voltage of that transistor. And with that basically difference, like the high threshold voltage as well as nominal threshold voltage, you can actually have considered 0 and 1. And also other, can also be encoded to more bits. So after some time, you're gonna also lose some of these electrons that you already trapped here. And that can actually bring you to this retention time error as well. So it's not only DRAM that has that problem. Many of these memory that they are based on like charge, they may lose that charge over time. For some memory is actually much faster, like DRAM. For flash memory is much slower, but it still is not also not infinite. So you cannot, so if you store data in your flash memory and don't access your flash memory for, I don't know, like 2 years or 3 years, then good luck with, having your data correctly. So that's not easy. So yeah, and as memory scales, as we discussed, it becomes unreliable. And this is the data that we observe from basically doing holistic evaluation on Facebook servers worldwide. That basically chips that they have higher density, they have the higher failure rate, which brings us to the same thing. Like when you increase the density and density of the memory chips, then the likelihood that they basically don't work well is going to be increased. So if you want to learn more about this analysis, this larger scale failure analysis of DRAM chips, you can check this paper in DSN 2015. So, I mean, these analyses and other stuff can be actually empowered by having some infrastructures. And in Safari, we actually build these infrastructures to understand such issues. Not only for DRAM, also we build infrastructures for SSDs and some other research topics as well. But yeah, I'd also like to remind you about one of the points that Professor Mutlu mentioned yesterday, that sometimes you need to build your infrastructure to empower your research. And this is actually one of the good example of that we basically build a FPGA system such that it can control DRAM low-level commands, like the timing of them, and also the sequence of them. And with that, you can actually, discover many of DRAM problems as well as also opportunities. So I want to show, for example, this work later that maybe you are already aware of RowHammer. This is actually the first RowHammer paper that we published. And it's actually, we use this infrastructure to show all the data of this work. So yeah, this is a system that we built. Like there are FPGAs and also a PC that I think control the FPGAs, and also a heater that can can provide the temperature, like the temperature control, and also a temperature control that works with that heater to arrange, to make sure that you have control on the temperature of the system. If you want to learn more about this infrastructure, I think you can talk to Hirai, Smile, Nisa, other folks that they are here. But this was SoftMC that we published in 2017 in HPCA. That is actually a flexible, easy to use C++ API and open source system. But we also work on it. And this is the new version of that, DRAM Bender, that Atterberg lead this project. And DRAM Bender provides much more functionality compared to SoftMC. Like it provides like 5 prototypes, 5 out-of-the-box FPGA-based prototypes. And it also supports both DDR3 and DDR4. Yeah, so with this kind of infrastructure, then you are able to basically learn more about your DRAM, as well as like the problems of DRAM and opportunities. I want to show you some of the analysis that for example, you can do with such a tool. So we have done an analysis on data retention in memory. And as we discussed previously, like DRAM cell has a retention time issue that after some time, the charge is going to be leaked, and then we need to refresh it. So the retention time profile of DRAM looks like this. Like many of the cells, actually, they can tolerate more than 256 milliseconds. There are sorry, there are some cells that basically they need retention time between 128 and 256 milliseconds, and only a very small portion of the DRAM DRAM cells need to be refreshed every 64 milliseconds. So we observe this data. Maybe something is wrong with this room. I'm also using. So, sorry. So yeah, only small portion of DRAM cells needs to be refreshed every 64 milliseconds. But when you design your DRAM, and also when you want to, tune your refresh rate, you usually need to work with the worst case. So that's why actually DRAM needs to be refreshed every 64 milliseconds. But once you have this data, you can actually design more intelligent controllers. You can basically intelligently only refresh those cells that they need to be refreshed every 64 milliseconds. For other cells, for example, you can actually refresh them less frequently. And that can heavily reduce energy consumption of the DRAM. So that's actually bringing me to my point, like when you design such infrastructure that you can learn about your DRAM chip and also your DRAM system, then you can actually understand the problems, and then also it gives you opportunity to design techniques such that you can benefit from those insights. And this is actually a great insight that we can reduce energy consumption. And we showed in this paper, Radar, that the title is Retention Aware Intelligent DRAM Refresh. So basically, you only refresh cells. Basically, you refresh cells based on the retention time of them. Of course, yes. It depends on basically like modules to another module. Yes. So basically, this needs to be profiled. So, so in this work, I think, I mean, Giray can, I guess, say better, but I think in this work, we consider that we have the profiling already. So you have the profiling data, and then based on that profiling data, you can apply such technique. But we also address the profiling issue in some of the later works. I think Minesh, for example, presented that in micro 2007. It was, I don't know, was micro or not, but yeah, around 2017, I guess. But that was a good question. Thank you. Yeah, so, and then we kept our analysis on data retention. I'm gonna just flash these slides. So if you're interested, you can learn more. We are also gonna have more, let's say, detailed lecture on these stuff later. But today, I just want to give you some idea about how, how much, how new designs can be empowered by having such infrastructure and also understanding your system. So, and then also we focus on how can we mitigate retention loss in many of prior work. This is one work from Samir Khan, and this one is also Avatar. And these are also different examples that you can look into it if you want. And yeah, this one is the rich profiler. This one was the work that I mentioned. From Minesh in ISCA 2017, that basically we work on profiling, how we can profile this retention time. Yeah, these are also some other works, recent works from Minesh. Minesh was actually a PhD student in Safari, but Now he's an assistant professor. I forgot the in Rutgers. Okay, so if you want to learn more about DRAM refresh, I would basically suggest that you check also this talk from Professor Mutlu. But now let me also talk about another issue that we discovered by using this infrastructure. So this one is actually from our ISCA 2014 paper that one can predictably induce errors in DRAM memory chips. So this is actually the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And people, wrote for this about like forget software. Now hackers are exploiting physics. So a lot of people were focusing too much on, let's say, software security. But then with all these, like this also is not the only problem that we have in hardware security, but it's one of the important one. RowHammer problem showed that people can also induce errors by using physics and learning by understanding how memory systems work. So this is the first RowHammer analysis that we published in ISCA 2014 that I'm gonna cover a little bit today. RowHammer. How many of you are already aware of RowHammer? Okay. Of course you are. You wrote a paper, I guess. Yeah, so this is the DRAM area. I'm not the best person to present RowHammer first, but yeah, I can try. This is the design, like the picture of the main memory, and like we have several rows of cells. So when you want to access a row, you need to open it. When you want to read a row or write to that row, you need to open it. And when you are done with that row, you basically close it by sending pre-charge command. So you open and then you close. And if you do this open and close, like activate and pre-charge frequently, like with a high rate, high frequency, you do activate pre-charge, then at some point you're gonna actually induce errors on adjacent rows. So this is we call hammered row, that you are hammering a row, and that hammered row can induce errors to adjacent rows. So this is like one of the disturbance errors that can read disturbance error that we discovered that in DRAM we have. And those rows that they experience errors, we call them victim rows. So repeatedly reading a row enough times before memory gets refreshed induce disturbance errors in adjacent rows in most real DRAM chips you can buy today. I mean, this data is for ISCA 2014, but I think still with the DRAM chips that we can buy as of today, we can also still observe the same thing. I mean, you need to be more creative in your hammered row and the way that you design your RowHammer attack, but still you should be able to induce errors. And we also show that in our recent studies. So this is the plot that we showed in 2014 that DRAM chips that we tested back then, like for the DRAM chips, DRAM modules in 2008 and until 2011, you rarely actually observe the errors. So there are some appearance that you can see from 2010 that you observe some errors in those DRAM chips. But when we actually move to more, let's say, recent DRAM chips as of the date that we were working on this project, we observe much more, which shows that when you make your DRAM more dense, basically this phenomena is getting worse. And that's also brings us to our point that DRAM has a scaling problem. So when you scale DRAM, it has energy issue, like because of the refresh time, because of the refreshing, that you need to refresh your DRAM more frequently, and also because of these like read disturbance errors like RowHammer, and also the failure rate. So this is the simple code that we wrote back then to show this phenomena, and we use our infrastructure. So essentially, this is a very simple code that we move a row to a register, and then we move another row of DRAM to the register. So this is to make sure that we basically, when we want to move this row, you need to activate. And then we want to make sure that we close that row, like by sending pre-charge command. So we need to access another row. So that's the reason we have two different rows. And also you need to avoid cache heat. So that's because we also use the instruction to flush the cache for both these rows. And then we need to do it iteratively. So by doing this code, like as I said, we avoid cache hits and we avoid row hits by changing between X and Y. We could actually induce errors in adjacent rows. And this is the data that we also, that's data we proposed. We showed in our paper that we observe errors with the access rate that we could achieve. And basically all the basic DRAM devices in 2012, 2013, most of them, they had these errors. So yeah, so basically, industry also looked into it, and they, I think Google also provided a much more sophisticated code. I'm not sure if you might be able to run this code in your system, but I'm not so sure. But you can, I think, download the code from Google and run on your system, and then let's see what happens. Yeah, so basically many RowHammer security exploits, like in our paper, we show that basically we have this RowHammer and this issue that one can induce errors in RowHammer. And then there were a lot of people that work on to exploiting these phenomena. And they show that basically one can exploit RowHammer to take over a system, read data they do not have access to, or break out of virtual machine sandboxes, corrupt important data, steal secret data, and so on and so forth. So basically, once you have some issue in your DRAM, in your main memory, then people can also be creative and exploit that issue and basically cause a lot of security issues. So in the end, those reliability issue that someone would think that, okay, RowHammer can be a reliability issue, but that can actually also cause a lot of security issues. So that makes it even more important to fix it. So if you want to basically learn more, also I would suggest to check this paper, like the robustness perspective from Professor Mutlu, and also this paper from in TCAT. We also published a survey on RowHammer. This is a recent update that Ataberk and Giray and Professor Mutlu published it. So you can also check it and learn a lot about recent RowHammer activities as well as old activities. Yes. Sure. I can also repeat because yeah, Giray successfully defended his PhD thesis. Congrats to him. And there is actually much, I think, extensive version of this in his PhD thesis. So feel free to check that as well. Yeah, also we checked that for analyze the study RowHammer in HBM chips because the study that we did in 2014 was only, I guess, DDR3. We also do the study on DDR4 later, but this is also a study that we have done on HBM chips that Ataberk has led this project. And I think we presented this work in the recent DSN 2024. This is also another actually read disturbance error that we discover in one of our work, RowPress, that Haosung has led this project. So we presented this work in ISCA 2023. We're gonna also cover this work later, but in RowHammer, we have to just like repeatedly, open and close a row, and that can cause errors in adjacent rows. But in RowPress, we show that if you keep a row active, or let's say, yeah, exactly. If you activate a row and keep it active for a long time, for long enough time, then that can actually induce errors to adjacent rows. And one of the things that we showed in RowPress is that actually RowPress can make RowHammer attack even worse. So in RowHammer, you need, for example, like activate and pre-charge a role, like for how many, like 1,000 times, is it a good estimation, like in RowHammer? Recent study, right? Around like 5,000. But with RowPress, we show that actually you can, reduce it to like tens of or hundreds of accesses. Oh yeah, actually, yeah, we even reduce it to one. So there were some people that they thought that RowHammer, like, is partially solved because, basically we cannot, so we need to activate and pre-charge our DRAM rows a lot to make that happen. But basically defense were powerful enough to avoid that. But with RowPress, we show that if you have RowPress on top of your RowHammer attack, you can actually, you can cause that error with only a few accesses, which makes RowHammer even more, let's say, problem. So now actually there are more works that they try to reduce the overhead of RowHammer defense when this hammer count is quite reduced. But yeah, you will learn about such things also in later lectures more. We also work on recent study of recent defense of the industry. So industry actually also has been, they try to address this problem. I mean, in the past they were just ignoring this problem, but at some point they try to, make a step in and provide some solutions. Recently in DDR5, they have an update in JDEC that they provide PRAC, which is a per row activation count. And that can actually, can be used to for RowHammer attacks. So we quickly, actually, immediately after this update in JDEC, we actually did a study on it. And we published a work in DRAM DRAM Security Workshop in ISCA 2024. That basically we provide a holistic analysis on using such command. So Osan has led this project. So if you want to learn more, you can talk to him. Maybe you can raise your hand. And you can correct me if I was wrong. So okay, so then basically our question is that, are solutions good? So maybe solutions are good if you have a narrow, view of the problem. But if you look a little bit wider, you can see there is kind of, some bypass path that you can actually bypass the solutions and cause problems. So that said, we need to be much more holistic in providing solutions, and you need to look wider and consider a lot of, conflicting problems to provide the correct solution. So key takeaways from these slides that read disturbance is a technology scaling problem, and finding a good solution to read disturbance is difficult and will become more so. So major trends affecting main memory, like DRAM scaling has already become very difficult, and increasing cell, and that's increased the cell leakage current, reduced cell reliability, and increasing manufacturing difficulties. And we also discuss all these issues in our papers. These are some examples that you can check. So it's difficult to significantly improve capacity and energy. And then we need to look into emerging memory technologies. And I'd like to remind you about the slide that we had yesterday, that there are plenty of room at the bottom and also plenty of room at the top of this computation hierarchy. And there are also much more if you can do if you work through the entire stack. So there are some emerging memory technologies, like different new technologies that you can actually benefit from them. But before also, it's still important that you look into your current technology and improve them as much as possible. Like with 3D stack DRAM, you can provide much higher bandwidths. With also this reduced the latency DRAM, like RLTL DRAM, is actually one of the work from us that we will discuss also in later lectures, that you can provide lower latency. Remember that access latency of DRAM has not been improved much in recent years. With this work, you can actually improve latency. And also providing low power DRAM like LPDDR3, LPDDR4, Voltron is actually a work from us that Giray, I think he was also one of the major co-authors. that provide much lower power consumption. But there are, so you should also be open-minded and look to other memory technologies, like non-volatile memory, that is also known as NVM. So we're gonna also have a lecture on non-volatile memory, like emerging memory technologies. But I mean, now briefly, we have like for some memory technologies like PCM, phase change memory, SCT-RAM, ReRAM, 3D Expoint, and so on and so forth. So these memory technologies also provide, for example, larger capacity, but all of them, they come with some, disadvantage as well. Like 3D stack DRAM, usually you have smaller capacity, even though it's 3D stack, and you can think that, okay, I can build on, and provide large capacity, but then you are gonna be bounded by the temperature control. So that's because actually 3D stack DRAM has a smaller capacity. But if you use 3D stack design with the technology that doesn't need, for example, refreshing, then you might be able actually to provide much higher capacity. So that said, I think understanding and improving the current technology can also lead to better design for emerging memory technologies as well. So basically the insight that you develop can be used in other systems and other memory technologies as well. So with reduced latency DRAM, we have higher cost. With low power DRAM, we have higher latency and higher cost. With non-volatile memory, usually they have higher latency, higher dynamic power, and lower endurance. And this lower endurance is actually one of the major issue of these non-volatile memories. Like basically, you cannot reliably write and update program and arrays, or say write to your memory chip more than some time. For example, with PCM, I think we are bounded by 10 to the power 8 or so, depending how you design your PCMs, like SLC, like you use each cell to store only 1 bit. Of course, if you use your cell to store like 2 bits, your endurance is even lower. In flash memory, I think we are even lower. We have much lower endurance. So basically, that brings us to reliability issue. So in the end, there isn't, I mean, as of now, maybe also in the future we might have, but it's very unlikely. But basically, we don't really have a technology or a system that everything is bright for that. So in the end, there are upside and downside. And as a computer architect, you should work on all these trade-off analysis and then design your system. So it's like design and space exploration is actually one of the interesting parts of computer architecture research. So like one of the idea that we can use is actually like having hybrid main memory. And actually is one of the major trends in our future systems. That, for example, in CPU, we can have a DRAM controller, and also we can have a PCM controller. And PCM is one of non-volatile memory, phase change memory. And then in DRAM controller, it can be, DRAM is fast and durable, but is a small, leaky, volatile, and high cost. But phase change memory is large, non-volatile, and low cost, but it is slow, it wears out, and high active energy. So then you need a kind of intelligent memory controller such that you can decide where to store your data. So then you need to basically come up with the solutions to how to map your data, how to intelligently map your data, how to migrate your data. And such things can be actually addressed with designing intelligent memory system, memory controllers, and so on and so forth. But yeah, so combining in hybrid memory design, which actually is, I would say, in a subset of bigger category, which is like heterogeneous system, that actually can be a very good idea. So when you have a heterogeneous system architecture, then you can actually combine different components that all of them, they have good things, but they also have bad things. But if you combine them and control them intelligently, hopefully you only benefit from good things and somehow handle the bad things of them, then you can actually have a much better system design. So hybrid main memory is one of the examples. We also have this hybrid storage that you can combine different storage devices with different characteristics. We have published a work on that, Sibyl, that Rakesh, where is Rakesh? Yeah, Rakesh was also one of the key authors in that work. That basically we manage a hybrid storage nicely, like where to map your data and how to migrate. Okay, any questions? Good. So, yeah, so as I said, main memory needs intelligent controllers. And industry is also writing papers about it too, which is good. So this is also the work from Samsung and Intel. Like, this is actually quite fascinating because these companies really don't work together much. But this work is like co-architecting controllers and DRAM to enhance the DRAM process scaling, which is quite fascinating. So it's actually one of the early kind of work from industry that shows that if basically processor people talk to DRAM people, and they can work together, they can make things much better. So, and a lot of issues that we have in our system is because different part of the system don't communicate, And I will show some slides in later today that how if you provide a channel such that you can communicate information from different levels of hierarchy, then you can actually enable much more better studies. This is also another work from SK Hynix related to RowHammer, I guess, defense. This is a controller that they designed, like they have this RowHammer counting cell, for example, RowHammer control. And so basically, industry is also trying to design intelligent controllers to, solve some of the issues, or at least try to solve some of the issues that we have in our current systems. This is also a work, DSAC from Samsung. Is also low-cost RowHammer mitigation using INDRAM stochastic and approximate counting algorithm. This is also a solution from Microsoft that you can check the paper from this link if you are interested. And this is the solution in DDR5 JDEC track that I already mentioned it. And after checking this basically link, you can also check our paper to see our analysis on that. That as I said, Osan has led this project, and he did a thorough analysis of PRAC on today DRAM systems. So, okay. Shall we take a break now, or? I like to give a break in 3 minutes, but I'm wondering if I continue, I'm not able to get to the good point in 3 minutes. So maybe let's have a break now, but let's be back by 2:12 precisely. Okay, let's get us started. I received one question during the break about how you can ask your questions related to labs and homeworks. I'm gonna basically provide some information during the second part of today's lecture that we will cover logistics. So yeah, I will discuss about that and keep your questions related to that for the second part. Giray also reminded me a great point that I want to bring it up. So this JTAG document is actually not free. It cost I don't know, $1,000 or so, which I'm not so sure. I mean the exact. At least 700. And if you open this document to understand the technique, good luck. I mean, it's not really easy because the description is quite, cryptic, and you need to spend a lot of time. So if you want to learn about such things, such a description of PRAC, this paper that we publish in DRAM security workshop is free. And also the description is much more, let's say, easier to follow and learn. So that's the beauty of open sourcing. You can learn about things much easier. Okay. So we discussed about RowHammer issues as one of the reasons that we need to look into the way that we are designing systems, and also the need for more intelligent memory controllers to avoid such issues. But there are also some other issues. So this is an orthogonal issue, which is about memory interference. That once you have multi-core system, and these cores are connecting to the main memory with a shared channel, so these cores interfere with each other when accessing shared main memory. And that's basically, if you don't control it well, it can lead to many problems like quality of service, performance issues. So this is also one issue that you might actually, you can have, and this has been shown in our research, and that actually calls for much better memory controller design. So the memory controller that we already have in our system is more or less like, trying to send the commands in a correct way, like obeying the timing of the data, which is actually, by itself is actually a hard task to do. But memory controller can also do much more. So it can be much more intelligent and can provide many solutions to the issues that we have. And if you compare the DRAM memory controller with flash controller that we have in SSD system, you can see that actually flash memory controller, like SSD controller, is much more advanced, and they do a lot of controlling and reliability tasks. So I think we also need to provide that information, and provide that insight in memory controller design and try to solve a lot of these scaling issues. So this is like the complex system that we actually have today, more or less. So there are multiple CPUs, and they can actually share a cache. We also have GPU, and also we can also have multiple hardware accelerators. They can be like DNN accelerator, for example. And all these can actually communicate with the DRAM and hybrid memory controllers, and that is connected to DRAM or hybrid memories. So essentially, you have heterogeneous agents that like CPUs, GPUs, and hardware accelerators. And you do need actually to understand the difference between them in your controller design, and try to hopefully make the whole system happy. And also we have like memory interference between CPUs and GPUs and hardware accelerators, which is an issue by itself, but it can be solved by designing more intelligent memory controllers. So it actually reminds us many goals and many constraints and many metrics. So, and how to allocate resources to heterogeneous agents to mitigate interference and provide predictable performance is actually a great research topic. So this is one of the work we have done in this area, like staged memory scheduling. It's for CPU, GPU system, which they are highly integrated. Like traditionally, CPUs and GPU are discrete. So like you consider discrete GPU that you connect GPU card on a PCI Express basically card. And then your CPU has its own memory channels, basically. But there are also a new design of integrated CPU GPU system that you essentially have CPU cores and GPU cores on the same chip. It's actually the case for NVIDIA, some chips of NVIDIA, as well as AMDs, as well as Intel. So for those systems, actually CPU and GPU, they are sharing the same memory subsystem. They are sharing the same memory channels, sharing the same like memory controllers. So, and most of the time GPU cause a lot of, like usually has much more frequent memory accesses. And those memory accesses can actually cause like the CPU accesses to be stalled or to be delayed. So GPU application are more or less latency tolerant. So they can tolerate latencies a little bit by switching between different warp or threads. But CPU applications are less latency tolerable, and they need actually much faster accesses. So handling all these basically requests with different characteristics from CPU and GPU, and also by considering the fact that CPU applications are more latency and sensitive, and GPU applications are more throughput sensitive. So handling by considering that in also mind is actually a tough task. But we have done some work in this area, in this staged memory scheduling. It's actually beautiful work from Rachata, and you can take a look and read it if you're interested. But we continue this line as well, like this work dash for heterogeneous systems, and some also more recent works. So the future is that memory controllers are critical to research, and they will become even more important. And they, as I said, they need to be intelligent. So this is actually one of the earliest works that to me was quite futuristic. That in 2008 or so, Professor Mutlu and his colleagues in Microsoft, and they work into design, they use reinforcement learning agents in order to design memory controllers. So that's actually quite, I would say, very much futuristic work back then. And now we are also using a reinforcement learning approach to design other parts of the system, like how we can design cache prefetching. That at some point we will cover that in this course. Or for example, how we can handle the hybrid storage system, so that reinforcement learning approach can help us. But this work was about learning about the application and also application request, and try to design the memory controllers based on that. So it's self-optimizing memory controller, which gets better as we use it. So yeah, and this is actually part of the research direction that Professor Mutlu is actually quite excited about, that which is data-driven architectures. So essentially, if you check the intelligent architectures, that the talk that Professor Mutlu delivered about how we should design intelligent architecture. So those architectures are those architectures that they can handle data well. And in that talk, Professor Mutlu mentioned that we need to have data-centric, data-driven, and data-aware architectures. So data-centric, you already know a little bit about it, and we're going to cover much more. And data-driven is actually, this is an example of that you use your data, your huge amount of data, to learn and basically make much better decisions in your system. And also another part of it is data-aware, that if you transfer the semantic of your data to your hardware, from the application to the hardware, then you can actually make much better decisions in the hardware. And we're gonna also see some examples in this lecture. So yeah, so all these things are very important, and I think it's increasingly important to make and follow in order to design architectures that they can actually, handle data much better and not get overwhelmed by the data. So we already covered some memory problems. Now let's take a look at how we can solve them. So we can actually have different approaches. One would be like fix it, like make memory and controllers more intelligent. So it can include like new interfaces design, functions, architectures, and like system and memory code design. We can also have another approach like eliminate or minimize it. So we can think of replacing like the DRAM with some other memory technologies, or more likely augment DRAM with different technology. So that involves new technologies and system-wide rethinking of memory and storage. Another approach could be embraced, like design heterogeneous memories, as we discussed, that none of which are perfect. So all of them have good and bad things. And then we need to map data intelligently across them. So how you basically manage, like handle this data mapping and data allocation, as well as data migration across your heterogeneous memory systems. And maybe there are some other ways also to handle. So any thought? Anything that's not covered in fix it, eliminate, or embrace? Yeah, think about it. So yeah, solutions to memory scaling require software, hardware, device cooperation. And that actually brings us again back to this, the importance of looking through the entire stack of computing to solve today's problems. So yeah, like solution one, I can give you some example, like new memory architecture. So we can overcome memory shortcomings with actually memory-centric system design. So at some point, you cannot actually scale memory much more to empower like the processor-centric design mindset. So if you benefit from memory-centric system design, the whole system would actually be much more balanced. And then you may not actually need that such, to push the boundary of the memory to the point that you cannot really tolerate the reliability. So memory-centric system design actually, to me, is a great solution to these problems. And the novel memory architectures, interfaces, functions, better waste management, like efficient utilization. And there are key issues to tackle in this area, like in how we can enable reliability at low cost, reduce energy, reduce latency, improve bandwidth, reduce waste, enable computation close to data. And this is I don't know if it's complete list, but some works that we have done in this area. It's very hard to read, but you can check them on the website, of course. These are the works that we have published in the solution that covers solution one, like new memory architectures. For the second solution, we can think of emerging memory technologies, like some emerging resistive memory technologies seem more scalable than DRAM, and they are non-volatile, which is good. So when they are non-volatile, that means that probably they don't really need to be refreshed. So when they are non-volatile, that means that you don't need to keep electricity on, to keep your data. But as I said, I mean, flash memory is also considered as non-volatile memory, but the retention time for flash memory is also not infinite. So at some point, you actually need to refresh flash memory to make sure that your data is not corrupted. So here we have an example of phase change memory, that data is stored by changing phase of material, and data read by detecting the material's resistance. So when you change the phase of your material, you're gonna have high resistance or low resistance. And based on that, you can actually encode it to 0 and 1. You can also encode it in more, let's say, accurate manner and have more bits per cell. Like for example, if you consider that you have only 2 levels of resistance, like low and high, you may call it like 1 and 0. But you can also consider that you have 4 levels of resistance, and then you can encode it to 2 bits. Or you can consider you have like 8 levels or 16 levels, and then you can have like, I don't know, 3 bits or 4 bits. Of course, at some point, your reliability is going to reduce a lot, and as well as your endurance. So again, is a trade-off analysis, like how much capacity you're getting by, increasing the number of levels in your read and writing, basically accuracy, but at the price of less reliability. So PCM is expected to scale to 9 nanometer, which is good, and also prototype at 20 nanometer, and expected to be denser than DRAM, which is actually by also considering that it can store multiple bits per cell, which I already explained. But emerging technologies have many shortcomings. Like, can they be enabled to replace, augment, or surpass DRAM? So there are a lot of issues with emerging memory technology, as I said, like upside and downside, that you really need to look into them in order to see how you can design your system to benefit from them. So this is one of the earliest work, I think, in this area that Professor Mutlu and basically his colleagues, they work on the architecting phase change memory as a scalable DRAM alternative. So yeah, so I think the idea in this work was that how we can use PCM as main memory. So what are all these decisions that you need to make at the system level in order to basically empower PCM to be your main memory? But if you read this paper, you will see that that's actually not easy. And in the end, probably kind of hybrid system design can be, better solution to have both PCM and DRAM, together. And that hybrid memory you can also think of having like DRAM as the cache for PCM, or you can also consider that the hybrid memory that PCM and DRAM, they are, each of them is a part of your address memory, like the memory address space. So they are a combination of them would fulfill your memory address space. So it's two different design of this hybrid system. So if you want to learn more about PCM as main memory, you can also check this paper. But this Intel Optane persistent memory also released in, I guess, 2019 or so. And that's actually non-volatile main memory based on 3D X-point technology. 3D X-point technology is very much similar to PCM in 3D design. But yeah, you could actually buy this DIMM, from the market, which is actually much more expensive compared to regular DRAM DIMMs. I don't remember the price. Anyone? Yeah, but it is expensive, more expensive as far as I can say. Sorry. Yeah, it's deprecated as. Yeah, exactly. That's also true. Yeah, but basically, Intel designed both actually 3D X-point technology, DIMM, that you can use 3D X-point as part of your main memory. And also they use this technology for SSD. So we also have some Intel Optane SSD that they use the same technology, and that SSD provides much smaller latency, lower latency compared to flash-based SSDs. But yeah, they also have their own shortcomings. And there are also some works that they study use of 3D X-point DRAM, a 3D X-point DIMM as a persistent memory in your system. So if you're interested, you can actually check those works out. So these are some works that we have published in the second solution, like emerging memory technologies, that you can check if you're interested. Yeah, so it is actually bringing me back to this design, like the hybrid memory systems that we can combine. Here is just an example, like DRAM, and for another technology, it can be technology X, like PCM. It doesn't need to be only two. Also, it can be several different technologies that you combine them together. So in the end, but you get the idea. Like you want to design a heterogeneous system that hopefully you benefit from the good things of different components together. So yeah, and also we like to exploit memory error tolerance with hybrid memory systems. Sometimes it's also not about, so you can actually, so you have DRAM and PCM, It can also be different DRAM banks that they have different reliability. And also the way that you can benefit from them is not only about latency difference, it's also about like the memory error tolerance. So that there are some applications, different applications that they have different error vulnerability. So how much they can tolerate errors. So if you know that basically, if you have that data, like this application has more vulnerable data, but application C has more basically tolerant data, then you can actually intelligently, map your data. Like your vulnerable data needs to be mapped to the reliable memory, and tolerant data can map to your basically low cost memory. So your low cost memory can be less reliable. So this is one example how you can benefit from this hybrid memory structure. And then you can have this heterogeneous reliability memory system, like HRM short. So this reliable memory is ECC protected and well-tested chips, but that low cost memory is like no ECC or parity and less tested chips. And we show that basically it reduce server hardware cost by 4.7% on Microsoft Web Search workload. And it achieves a single server availability target of 99.9%. So you can actually achieve good availability if you map your data nicely. Of course, if you map your vulnerable data to your low-cost memory, then the availability of your server is going to be so low. But if you are intelligent enough, like the memory controller needs to be intelligent enough such that it can map your data by having this information. So that's why we are thinking that if you transfer your semantic of your data and what are your data. So in the memory controller, usually we don't really know if there is a difference between different memory addresses or different data. So the hardware is actually treating everything like a memory row, right? So if you transfer that information somehow to your hardware, then actually memory controller can make such decision, like, and then you can get much better reduced cost as well as also at the price of no availability loss, basically. So yeah, so this heterogeneous reliability memory, at step one, you need to characterize and classify applications' memory error tolerance. So you can actually have a spectrum of that, like vulnerable to tolerant. And then once you have this profiling result, you can map allocation data to this HRM system enabled by software hardware cooperating solutions. So yeah, you can, again, also you can have a spectrum on designing, like reliable should be reliable memory plus like parity memory plus software recovery. And then you have low cost memory, which is unreliable. But hopefully it's not gonna impose you basically reliability issues because you intelligently map data that they don't need such reliable storage to that part. And this is also an evaluation result using Radar chart. Radar chart is a chart that you can have when you want to actually see is your trade-off good or not. Sometimes you can use Radar chart. So basically, there are different points in it, like different scales, like crashes, server per month, memory cost saving, incorrect per million, basically the number of incorrect per million queries, and single server availability as well as server hardware cost savings. So basically the technique that provides the larger area is probably going to be the better trade-off. And you will see that basically in this scale, like inner is worse and outer is better. So HRM is one of the best trade-off in these comparison points. So if you want to learn more about this work, I would suggest that you check this paper from DSN 2014. But this HRM is only as an example of our insight that to achieve the highest energy efficiency and performance, we must take the expanded view of computer architecture that we already discussed about it today and also yesterday. So, and another example in this area is also IEDM for DNNs. So deep neural network evaluation is very DRAM intensive, especially for large networks. Some data and layers in DNNs are very tolerant to errors. And we can actually, once you have that information, you can map such data and layers to low energy, low latency DRAM, which may have more errors. So you can actually reduce, timing of your DRAM, and that can actually cause better energy as well as better latency, but it can come at the price of more errors. So if you intelligently map layers and data of your DNN that they don't need very reliable DRAM to those unreliable DRAM parts, you can actually save energy and also improve performance. So, but you need to actually do that profiling to have that data and then intelligently map your information. This again bring me to this example of, transferring the information from the software, like the semantic, to the hardware can improve performance. So this is data that we report in Eden paper. So basically there are some, this is data from different weights and in ResNet 50. And you can see that like the maximum tolerable bit error rate. So there are some parts that they are much more basically reliable, and some parts that they are less reliable. I mean, they less tolerable. So for those that are more tolerable, we can map them to faulty, let's say, DRAM regions. So in Eden, this is an overview of this work. That key idea is enable accurate, efficient DNN inference using approximate DRAM. So Eden is an iterative process that has 3 key steps. In first, we do some boosting DNN errors tolerance, which is a software part of this work that we work on, the model itself to boost DNN error tolerance. At the second step, we basically we characterize DNN error tolerance. And once we are done with the first and second, we can do this DNN to DRAM mapping. And then we can map to basically different DRAM regions, like the reliable region of DRAM or less, like more faulty regions. And on average, we show that we can basically provide 21% energy reduction, maintaining accuracy within 1% of original implementation. And on average, it provides 8% system speed up. And some workloads actually achieve 17% speed up. And Eden achieved actually close to the ideal speed up. So in ideal, we consider that I think TRCD is like one of the like DRAM timing parameters, and TRCD is 0. So we set TRCD to 0 just to see that what's the gap of the, using such ideas. And we observe that with Eden, we can actually get to ideal result with a close margin, which is good. So that shows that we can actually, bridge this gap nicely by using a bit more intelligent system or, memory controller design. We also show the benefit of using this Eden idea on other platform like GPU, Iris, which is an accelerator designed for DNNs, as well as TPU. And we show basically energy reduction on all these systems as well. So if you want to learn more about this work, please check this link. It's going to be also part of our readings like this, I guess, one of the required reading in future homework. So at some point, I think you need to basically review this paper as well. So better you start sooner. Okay, so, but this idea that I already mentioned, this idea and also that reliability, like a very heterogeneous design, these are part of this subset of this architecture, data-aware architectures that we already discussed. And this is like computing architectures today, as we said, are terrible at dealing with data. And they designed to mainly store and move data versus to compute. So that brings us to data-centric architectures, that we want to move on from processor-centric to data-centric architectures. And today, architectures are terrible at taking advantage of vast amounts of data. So more or less, we mostly have designed to make simple decisions and ignoring lots of data. So once you want to design your policy, you have some set of workloads, and then you try to make a decision like that could work for those workloads, maybe on the average case. But that doesn't say anything about future workloads. And also, more or less, you need to design for the average case. But why should we limit it to that? Why not try to adapt your system to the best thing that can be for that workload? So that brings us to this, instead of having human-driven decisions, we can have data-driven decisions by benefiting from machine learning algorithms such that they can benefit and learn from the characteristics of the data, and then try to optimize your decisions, your policies, as we run the application. So that can hopefully, provide the best, almost best, which, I mean, best is a very strong word to say, but yeah, a good performance for every workload that we test, not only for average workloads or average of workloads that you have tested in your design time. So that's data-driven decisions that we're gonna also see much more in future lectures. But the third point that I want to talk about a little bit more now is about that today's architectures are terrible at knowing and exploiting different properties of application data. So designed to treat all data as the same, as I said, and they make component-aware decisions versus data-aware. So like Eden was an example. Like once you basically transfer that information that, okay, some weights, some layers, they don't really need high reliable memory regions. So once your hardware is aware of that information, then can provide much more intelligent decisions. So the data-aware architectures, like it understands what it can do with and to each piece of data, and it makes use of different properties of data to improve performance, efficiency, and other metrics. And it can be like includes like compressibility, approximability. Like approximability is exactly like Eden. Like we use this design this approximate computing, by knowing that some of the parts of your DNN does not need such high reliable memory regions. Or for example, sometimes capturing the locality in your accesses, in your memory accesses, is not easy. But once you basically transfer the information about your data pattern, like the access pattern, to the hardware, then actually caches can also benefit from it. And your cache controller can, can do much better for capturing the locality of your accesses. And also, once you know the sparsity, you can, design better systems. And criticality for computation X. Sometimes you know that this computation in function is much more critical, or this thread at this moment is much more critical. So once you know that information, you can prioritize that thread or make some decisions to prioritize that computation. And also like access semantics and security and privacy and many more. So yes. Uh-huh. Yeah.
So the question goes like, the current dominant paradigm is electrons.
Mm-hmm.
So what other options do we have?
Yeah.
Like what other ways?
Yeah. Okay. So for a live audience, the question is about the most of the computing architecture today is based on electrons, like exactly the transform hierarchy that I showed. But the question is about what are other also versions of computing or different technologies. So yeah, I think the answer is partially actually in the question. Like yes, we can also use biology, like DNNs to do computation. Also, there are huge like effort on using quantum computing for doing computation. There can be some other thing that I'm not remember now, that I don't remember now. But the thing is that all these computation paradigm, they also have good and bad things. So it's very hard to imagine that one computation paradigm is gonna be the future. So in the end, we're gonna benefit. We should actually benefit from good things of different computing paradigm. Like for example, quantum computing has been shown that they can provide quite fast like performance, and they can provide especially for those applications that they have like exponentially complexity in our common way of computing. But these quantum computing is actually much less reliable, and people have been working on that to provide to add a lot of complexity to the system to make them reliable. So in the end, I think we're going to actually have a mix of different computing platforms. And the idea of heterogeneous system is actually, I would say that would beat everything. So in the end, we need to benefit from heterogeneity in our design decisions. Thank you. So the problem that we have is that we have limited expressiveness. So like higher level information is not visible to hardware, as I said. So you have like, for example, at the software, you have data structures, you have code optimizations, you have access patterns, like especially in graph workloads. I mean, capturing the locality at hardware is actually quite hard. So at hardware, you may see that your graph accesses is more or less random, but it might not be that random as well. I mean, once you know that you're operating on a graph and you can predict what's going to be the next node that you're going to reach, and if you transfer that information to the hardware, you can actually predict your next access better, and hopefully, like you can, for example, use it for prefetching. Yeah, so these are the whole information, like, and also these are some examples, the information that we have at the higher level, at the software level, but at the hardware, everything is just 1 and 0, like, and we operate with instructions and memory addresses. So that is not good, for sure. So basically, our solution is that we need to have more expressive interface. So we want, at the software level, we want to basically have some, higher level program semantics to be transferred to the hardware. And for that, we need to design some basically system, the way that how we can communicate. And this expressive memory, XMEM, is actually one of the work that we have published in this area, and I'm gonna cover it a little bit today. So this work, expressive interfaces, is for a case for richer cross-layer abstractions, like bridging the semantic gap with expressive memory. So software provides key program information to hardware, like data structures, access patterns, and data type. Like data type also, you have integer, float, char, double, character, and all these things, they don't really matter at hardware. So, I mean, but if you express them to the hardware, you can make much better decisions. So for data structures and access pattern, for example, you can use them for better data placement, or for better prefetching, more accurate data prefetching. So I'm just using prefetching, and I assume that everyone knows what I'm talking about. Do you know what is like cache prefetching, cache data prefetching? No one knows? Okay, someone. Yeah, so basically prefetching is actually very simple, is that you can bring your data or your memory address ahead of time, such that when you need that in your cache, you find it there. So you don't really wait for that memory address that you access your cache, and then you encounter a miss, and then you need to wait for miss penalty to bring your data to cache. So if you can somehow predict your future accesses, and then you bring data ahead of time to your caches, and that doesn't need to be only data, it can be also instructions. So you can do instruction prefetching to your caches, then you can actually hide latency by that. So once you know your data structures and access pattern, you can improve your prefetchers. So you can improve the accuracy of your prefetching and providing better coverage as well. By knowing data layouts, you can also design better data compression, for example. So once you know that, my data is only 4 bits, and then you are wasting 32-bit register for your data. So it's clearly, there's a problem here, right? So once your system knows about it, then you can actually nicely compress your data, and then you can even design your hardware for 4 bits, for example. You can have ALUs for 4 bits, which is actually happening these days in order to, provide better energy efficiency and performance for, let's say, machine learning, for example. So yeah, so we want to enable many cross-layer optimizations. It can be like we want to express like data structures, access semantics, data types, working set, reuse of data, access frequency, and so on and so forth. And then there can be a lot of optimizations that the hardware can make, like cache management, data placement in DRAM, data compression, approximation, DRAM cache management, NVM management, NUCA, NUMA optimization, and so on and so forth. And all these, in the end, they can benefit, can have more efficient hardware, better performance, and reduce software burden, like ease of programmability and portability in your systems. So yeah, so our approach is, as I said, rich cross-layer abstractions. And then with this cross-layer abstraction cross interface, you can communicate that information from program to the hardware. And then in the hardware, you can make decisions related to your application. So this is an example like XMEM that I said, like the goal is to convey data semantics to the hardware that enables more intelligent management of resources. And XMEM introduces a new hardware software abstraction called Atom for conveying data semantics. And yeah, essentially you can communicate that to the hardware from the software, and then hardware can, as I said, make intelligent decisions. So if you want to learn about more, let's say, like aids and enables that many optimizations, like XMEM enables many optimization in the system, you can actually check this table and also the paper as well. Like, as I said, like memory optimization, like cache management, page replacement in DRAM, and like the semantic that provided. Like, for example, for cache management, we can distinguish between data structures or pools of similar data, and working set size, data reuse. So when we basically provide these semantics, then we can enable like applying different caching policies to different data structures or pools of data. We can avoid cache trashing by knowing the active working set size. Or for example, we can bypass or prioritize data that has no or high reuse, for example. So yeah, this is just an example, but yeah, if you check this table, you can find a lot of interesting insights. And this is a paper that I basically refer everyone to this. I think this paper also going to be one of the reading in our future homeworks. We have done also this basically richer interface for GPU as well. This is the work, the locality descriptor, a holistic cross-layer abstraction to express data locality in GPUs. So for GPU, actually, data locality is even harder. And usually, if you capture the L1 cache hit rate in GPUs, you're going to see that hit rate is actually quite low. So in CPUs, yeah, if I want to just give some number, it can be like the hit rate usually is much more than 90%. So CPUs actually L1 cache hit rate is quite good. But in GPUs is usually around like 50%, 60%, 70%. So it's much lower compared to CPU. There is a reason for that as well, because GPUs are designed, so the GPU idea is that they don't want to, as a first primary goal, is not to reduce memory latency by using caches. It's about provide the infrastructure that you can hide memory latencies by quickly switching between different threads. But it turns out that that's not enough. And a lot of data from research as well as NVIDIA that shows that we are bonded a lot with the memory accesses. So that's why actually NVIDIA also and other vendors, they try to improve the caching in the GPUs. Like, for example, in 2009, I guess, NVIDIA introduced L2 cache. So before that, we didn't really have L2 cache in GPUs. And now also, they are increasing the large size of that L2 cache a lot. So basically, in the end, the world is not beautiful for every single idea. So in the end, you need to benefit from different ideas, as I say, in a heterogeneous design to hopefully make the whole system better. So yeah, this is also a locality descriptor for GPU. As I said, like we want to exploit data locality in GPUs. As I say, is quite challenging. And so we at the application, we have this software, and then we have locality descriptor that transfers information that can be used for data placement, cache management, CTA, which is thread block, cooperative thread array is a NVIDIA terminology, if I'm not mistaken, and data prefetching to the GPU. So, and yeah, this is like the application is flexible and architecture agnostic interface, and then we can have this access to program semantics using this locality descriptor. And we show that we can benefit performance like 26.6% up to around 47% from cache locality, and around 54% on average from NUMA locality. This is a more recent version of that work that we proposed, MetaSys, which is a FPGA prototype for expressive memory. That if you want to learn more about this work, you can check the link. But I think at some point we will also present this work a little bit in one of the lectures. Okay, so yeah, and these are like heterogeneous reliability memory that I already discussed about it. These are also example of data-aware architectures. IEDM that I already talked about it, again, is data-aware efficient DNN inference. SMASH, which Konstantinos has led this work, is like software hardware indexing acceleration for sparse, basically matrix operations, which is quite important for graph applications. Data-aware virtual memory framework. This is also the work that we show that basically virtual memory framework was not really aware of data semantics. And this work, Nasran, showed that with this VBI, you can provide more understanding of your application to your virtual memory system. And then that can be used to improve performance and make better decisions. Software hardware climate modeling accelerator that Gagan has led this project. Hardware software time series analysis accelerator. Is another example of data-aware architectures. FPGA-based processing near memory, accelerating linked data structures. Accelerating approximate string matching, which we show that. So once this work, GenAsm is actually a new algorithm, as well as the architecture that can benefit from that algorithm. So it's like hardware software co-design that once you design for the entire stack, then you can actually provide much more benefit. If you want to learn also more about accelerating genome analysis, you can check this paper from Mohammed Al-Sir. But we're going to also have a lecture specifically on genome analysis later in this course. We also show that how we can benefit from hardware software co-design in order to accelerate graph applications on PIM. This is a work that we published in 2015. This is also another work that we have done with our collaborators from Professor Thorsten group. And we show that basically, once you use different algorithm, like for graph applications, there's a theory on graph applications that if you use linear algebra or also set algebra, you can actually implement your graph algorithms with basically using algebra, using set algebra or linear algebra. So those algorithms might not be actually beneficial for processor-centric design, especially, for example, with linear algebra, as far as I can say, usually the complexity of the algorithm increased when you implement with linear algebra. But once you are using PIM system, things can be changed, right? For example, with set algebra, you're gonna encounter a lot of bulk bitwise operations. So when you use a set algebra, you can implement a lot of graph mining applications with using operations in sets, which like union of sets, and what's the other of intersection? Thank you. Union and intersection of sets. So basically, union is actually going to be translate to OR operation in the hardware, and intersection is going to translate to AND operation. So it's going to be bulk piecewise operation. So you're going to learn about some processing using memory technique that they can actually benefit fast bulk piecewise operation inside the DRAM. So once you implement your graph applications using those bulk piecewise operation with AND and OR operation, you can easily implement them in processing using memory. And that shows actually with changing the algorithm for the hardware that you have, again, hardware software co-design, you can actually provide much better performance in the system. And also we show that processing memory is not only beneficial for, let's say, server workload, server system, enterprise system. They are actually important for, I would say, every kind of systems. So for edge devices that they are also quite limited in energy consumption, we show that processing memory can really benefit mobile workloads. And I think I showed in numbers from this paper that basically around 60% of the energy of the whole system is consumed on data movement. And with PIM, you can actually eliminate or reduce that energy consumption a lot. So the challenge and opportunity for future is that we need data-aware, expressive computing architectures, and we need to rethink the entire stack, and we can get there case by case. Okay, so let's have another break until 15:15, and we will continue from here. Thank you. Today, no. But later, yes. See. Okay, let's continue. So we discussed about a lot of issues that we have in memory, and also about the opportunities that like by understanding these issues and gaining insight, you can actually design much more better systems using in data-aware architectures as well as data-driven and data-centric design. But I also want to change the gear a little bit, that essentially you also need to design, have frameworks, have systems such that you can simulate and evaluate your ideas. And we're going to also hopefully have a lecture on simulations in general and why is it important and how we can design simulators. But in these few slides, I want to just give you an idea about that very, very quickly. But yeah, essentially, you need to be able to simulate your systems, but here with the focus on memory. So this is the simulator that we designed in around 10 years ago. RAMulator, a fast and extensible DRAM simulator. So with this, we had some motivation back then that DRAM and memory controller landscape is changing. And also there are many new and upcoming standards and many new controller designs. So we wanted to have a fast and easy to extend simulator that basically we can enable analysis on all these, different DRAM technologies, DRAM interfaces, as well as also to test our ideas. Once you want to make some changes in the memory controller or also in the DRAM subsystem, how you can basically evaluate it. So yeah, and in this table, you can actually see the landscape of DRAM-based memory as of 2015. Like the commodity DRAM, we had this DDR3 and DDR4. And also for low power, we had this LPDDR3, LPDDR4. For graphics processing unit GPUs, for example, we had GDDR5 back then. Now we have like GDDR6 or so, HBM, many more. And also for the performance, we have different also memory technologies like different kind of DRAM cells like EDRAM, embedded DRAM, and also 3D stack designs. And also there are many works in academic that you should be able to study them, analyze them, and see the effect, like the benefit of them. So all these are like the motivation of having such tool, that we designed this tool and we provide out-of-the-box support for many DRAM standards. And so we also compared RAMulator with other basically memory models or memory simulator back then. And we actually showed that RAMulator is much more beneficial, and you can basically, it covers a large body of like DRAM technologies, DRAM interfaces, as well as academic works. And it was 2.5 faster than fastest open source simulator back then. And also it was modular and so extensible to different standards. So we used that RAMulator to, for example, do the case study, like comparison of DRAM standards. So for example, this analysis is empowered by such tool. It's almost impossible to do such analysis using your real system. For example, your system, if you want to do it with real system, so in your system, you have a CPU, and that CPU might work with DDR4, for example. So you cannot really study DDR3, for example. Also, you cannot study LPDDR. So if you want to study LPDDR, you need to change your system. And once you change your system, there are many, many other conflicting features that they are also changing. So in the end, your data that you can capture from real system analysis for these standards is not really meaningful, because by changing your system, you are causing a lot of other changes, as well as not only like the standard. But with this simulator, we can only consider that, okay, the CPU design is fixed. Your DRAM size, for example, is fixed. Other part of system is fixed. And the only thing that you are changing is actually like the standard. And then you can see the effect of that standard change, in your performance analysis. So that's the beauty of having simulators, actually. And they are very much needed for doing computer architecture research. So yeah, we observed that, the IPC, like instruction per cycle distribution, and these are normalized to DDR3. And we basically tested like all these DRAM standards like DDR4. SALP is a sub-array level parallelism. It's actually one of the works from Safari from Professor Mutlu. That basically, we're going to also discuss it in some of the future lectures. LPDDR3, LPDDR4, GDDR, HBM, and so on and so forth. So recently, we also extend this RAMulator to RAMulator 2.0, and we publish also the extended version of it. So you can find this paper on this link, archive, and it's also open source on this GitHub link. So there is an optional assignment for you for RAMulator 2 that you should, review. You can, it's an optional assignment. It's not mandatory. So you can review the RAMulator 2.0 paper and email Professor Mutlu your review. You can also CC me. And also you should download and run RAMulator 2.0 and compare DDR4, LPDDR5, and HBM2 for benchmarks of your choice. And all these benchmarks are provided in RAMulator repository. And then you can email your report to us. And this can help you get into memory system research quickly. So you can, if you're interested, you can do it. And there might be also some credit for this optional homework. So we also published some, case studies in RAMulator 2. Like there are a lot of these RowHammer defense technique, like Para, Hydra, Graphene, RRS, and Ideal, which I'm, here I can say what is Ideal here.
That's the physical mechanism
Uh-huh.
that transforms
Okay.
it's like the
Yeah. So Ideal technique is a baseline that we consider that we can send RowHammer preventive refresh when it's actually needed. So for many works, when we send that commands, we actually cause some performance overhead as well, right? So if you issue that preventive refresh more often or more frequently, then yes, you can avoid RowHammer, but at the price of huge performance overhead. So with Ideal, basically you only issue that command when it's needed, when it's actually needed. And then comparing with Ideal, you can see the gap, basically. It's always good that we come up with some Ideal or Oracle design that can show the gap between and how much the headroom, to improve our system or design. So we have done this analysis in our RAMulator 2, and all these basically mitigation techniques are included in RAMulator 2. So you can just check them quickly. Yeah, this is also another study that we use RAMulator 2 and performance evaluation of DDR5 for per row activation, like PRAC. As I said, Olsan's work in DRAM security. You can use, we use RAMulator 2 to implement PRAC and evaluate it. So that's the beauty of having such, tools, which you can quickly implement different idea and test. So what we will cover in the next several lectures, this is the agenda for the next several lectures. So we're going to have lectures on computation in memory, like processing in and near memory, which is going to cover data-centric architectures. We're going to see some key issues of data retention and memory interference. We're going to have lectures on RowHammer, like memory reliability and security, how we can provide low latency memory. Remember that improving latency in DRAM is actually challenging. So how we can come up with better latency in DRAM is quite interesting. Data-driven and data-aware architectures, memory controllers and memory quality of service, and guiding principles and research topics. So these are some topics, more or less, that we're going to cover in this course. So if you want to learn more about PIM, I would suggest that you check this book chapter. As I said, we're hopefully going to release the new version of it also soon, so stay tuned for that. And this is also another like review that is more or less like workload-driven perspective. So you can also check this paper if you're interested. And this is also an early position paper from Professor Mutlu that about memory scaling, a system architecture perspective that you can take a look. And there's a more extended version of that you can check in this book chapter. If you want to learn more about RowHammer survey, you can check this one or the related work of Giray's PhD thesis. And this is, again, RowHammer survey. So we also discuss about challenges in memory scaling, like the data retention, reliability and vulnerability, latency and parallelism, energy and power consumption, memory's inability to do anything more than just store data. And we're going to tackle all these issues in this course. Okay. So can we switch to the next lecture? Any questions? Is it about?
Is there a weekly division? Like how many?
So you can actually get that idea by checking the last year or last editions of this course. Yeah, so it really also depends. There are some semesters that we focus on some topics more. So it also depends on how topics are getting hot. But I think we're going to have 2 or 3 lectures on processing memory, for example. And then I think 4 lectures about DRAM reliability and also these retention time, scaling issues of DRAM. But yeah, you can get the idea, hopefully, from last year editions. Okay, any other questions? Are you interested? Okay. Okay. Okay, great. So now let's look into our course info and logistics. It's going to be quick, and I think we are early today. So that's good. So yeah, this course is taught by Professor Mutlu. He actually provided background about him yesterday. So I'm not going to repeat it again. But yeah, Professor Mutlu is a full professor at ETH Zurich since September 2015. And he's been working on different research, quite a lot of topics, as you can see here. Computer architecture, systems, hardware security, and bioinformatics. We have a lot of other also teaching assistants. So I'm Mohammed, as you know, hopefully. I'm also one of the instructors in this course. But there are plenty of teaching assistants that they are helping us. Konstantina is the head TA of this course. Maybe you can raise your hand. So if you have any issue that you want to get resolved, you can, of course, approach Konstantina. And we have other also TAs, including senior researchers, as well as PhD students, some master students and interns that they are working with us. You're going to get to know them more and more in the future as well. So our goals of this course is that we want to teach, enable, and empower you to understand how a computing platform works, understand how decisions made in hardware affect the how decision made in hardware affect the software programmer as well as the hardware designer, and how to think critically in solving problems. So you're gonna actually see a lot in this course that whenever Professor Mutlu or the lecturer discuss an idea or present a paper, then immediately after that, we're going to have a slide that we're going to analyze. Like, what are the strengths of this work? What are the weaknesses? And how can we do better, basically? And then that's actually a practice that we're going to do, we're going to have in these lectures a lot. How we can think broadly across the levels of transformation that we have seen some examples today, but we're going to see a lot during this course, and how to understand basically understand how to analyze and make trade-offs in design, and apply the above in several lab projects and homeworks, basically. So the major high-level goals of this course is to understand the principle of designs, understand the precedents. Based on such understanding, you are enabled to enable you to evaluate trade-offs of different designs and ideas, enable you to develop principled designs, enable you to develop novel out-of-the-box designs. And the focus is on principles, precedents, and how to use them for new designs in computer architecture, of course. So regardless of your future direction, learning the principles and methodical analysis techniques we cover will be useful to design better hardware, design better software, design better systems, make better trade-offs in design, understand why computers behave the way they do, solve problems better, and think in parallel, think critically, and so on and so forth. So a note on hardware versus software. Sometimes I can see that people, consider this course as a computer hardware, but essentially computer architecture is much more than that. So you will be much more capable if you master both hardware and software and the interface between them. So you can develop better software if you understand the hardware, and you can design better hardware if you understand the software, and you can design a better computing system if you understand both. So again, that bring us back to this transformation hierarchy and the importance of having this expanded view of computer architecture. So now let me share some expectation that we have. So there are some required backgrounds like digital circuit course, programming, and open mind, willing to take in many exciting concepts, and also learn the material thoroughly. So you need to attend lectures, do the readings, and do the exercises and do the labs. As Professor Mutlu mentioned, attending lectures in person is preferable, but you can also attend over Zoom. You can watch lectures over, YouTube. You can also attend lectures, after that, because our lectures will be live stream and will be kept on YouTube. So you can also watch them later. But make sure that you follow a way that benefits you more, basically, In my opinion, attending lectures in person is much better because you can interact much better. But yeah, feel free to choose the way which suits you better. Of course, you need to work hard in this work, and this course will be hard, but fun and informative course, hopefully for you. And you need to basically ask questions, take notes, participate, essentially, and perform the assigned readings. Please also participate online, like lectures and for Moodle. So for all of our labs, homeworks, as well as for lectures, we're gonna have Moodle From, like the Moodle overflow, like the From that you can use that for Q&A. So for whenever you, for example, you have a question on the lab that you are doing or on the homework that you are doing, you can just go to that form and ask, like the corresponding form, and ask your questions. And our TAs will get back to you in 24 hours. So that's our basically standard. And for each lecture, we're gonna also have a form. So for example, later when you review this lecture, you encounter some issues, you have some questions that is related to this lecture. So you can just go to that form and ask your questions, and then hopefully we're gonna get back to you in 24 hours. So yeah, try to use all these resources to participate, make and ask questions, discuss. And also in labs, yeah, like the forums that we have is not only, so they are not only meant to be, the part that you ask questions and we answer. So sometimes if you see a question there and from one of your colleague and you know the answer, you can also reply and share. Of course, TAs will also check your replies, and if the reply is correct, we can actually certify, like verify it, or sometimes we can improve that answer. But make sure that you use it for discussion as well. So it's not only about that you ask question and TAs answer. So it's gonna be like back and forth discussion that we can have. So yeah, and of course, try to start early. I mean, labs take time. So if you just push them to the end of the semester or for the late deadline, you're gonna encounter issues basically. So make sure you start early in all these tasks. And if you want feedback, also you can come to our office hours. We're gonna announce office hours hopefully today or over weekend. I think we will have 2 office hours per week. One slot on Monday and one slot on Tuesday, if I'm not mistaken. These office hours are going to be hybrid and online. So you will get the whole information, like the Zoom link and also the actual office that you can also come to ask your questions. And office hours are brilliant in order to come to discuss with TAs, ask questions. So yeah, I would very much encourage everyone to benefit from such office hours. And remember this quote for posture, that chance favors the prepared mind, that Professor Mutlu mentioned yesterday. So you should basically, how you prepare and manage your time is very important. There will be many lab and homework assignments, and all of them will take time. So as I said, start early and work hard. We're gonna have, I think, 6 labs. 2 of them, as far as I know, they are bonus. But bonus labs are also good for you for learning as also for getting better grades. So, for example, if you lose some parts of your grade in homeworks, for example, you can compensate by doing basically bonus labs. So yeah, this will be a heavy course, as you can imagine, more or less. But however, you will learn a lot of fascinating topics and understand how a computing platform works. And it will hopefully change how you look at and think about designs around you. So how will you be evaluated? This is basically our grading. So as Professor Mutlu also mentioned yesterday, this course is not very much, exam oriented. It's actually more or less lab oriented. So 50% of your grades coming from lab assignments. So when I say that we have 6 labs and 2 of them are bonus, means that if you do 4 labs completely, like get the full mark on 4 labs, you're gonna get the 50% of your grade. But you can do, bonus labs, hopefully to compensate some of your loss in some other parts. We're gonna have final exam, which is, it has like 30% of your grade. So final exam will be in this room, but I mean not necessarily this room. We might need to reserve another room if needed, but essentially it's gonna be in the same slot. So it's I think we're gonna have, yes, I think I can announce it as of now. So the final exam would be on Thursday before the Christmas break. So which is gonna be December, someone can say. Yeah, December 19th. It's gonna be our final exam. We're gonna also have a lecture on December 20 as the last lecture, but for some other fascinating topics. But yeah, our final exam will be on Thursday, December 19th. We're gonna also have 5 homeworks that they will count for 20% of your total grade. And there are, as I said, many extra credit possibilities in homeworks, labs, and exam. So as also Professor Mutlu mentioned, if you really work hard and you do the labs and getting really high grade in this course is not hard. So yeah, so this is kind of the course that if you really work hard, you will also get the reward. I mean, if your focus is on grading, but I'm pretty sure that if you are working hard, your focus is much more than grading. Okay, so these are our course goals that I'm gonna mention them again. Like the first goal is to familiarize those interested in computer system design with both fundamental operation principles and design trade-offs of processor, memory, and platform architectures in today's systems. We have a strong emphasis on fundamentals, design trade-offs, and key current and future issues. A strong emphasis on looking backward and forward and up and down. The second goal is to provide the necessary background and experience to design, implement, and evaluate a modern processor by performing hands-on simulator implementation. So that those labs will help you. Basically, we have labs on, as I said, like RAMulator 2.0, as well as labs on ChampSim, which is one of the simulators that you can use if you want, for example, test some idea for processor. I think you're gonna use ChampSim for implementing cache prefetching techniques and many other simulators. Like the lab one that we're gonna release, I guess, today, and you will have, I guess, 3 weeks to deliver lab one, is actually about cache simulator. So you're designing a simulator for cache. And then you can use your simulator to test different cache systems. Yeah, so as I said, you have a strong emphasis on functionality, hands-on design, as well as implementation and efficiency. And a strong emphasis on making things work and realizing ideas. So one thing that I forgot to mention about homeworks and labs, let me also say it now. So yeah, so as I said, for every homework and every lab, we're gonna have a course like Moodle form that you can go there and ask your questions. Homeworks have usually, have 2 parts. The first part of homework is paper reviews. You're gonna receive an email to our hot CRP review system that you will register to that hot CRP, and then basically the papers that you need to review them will be assigned you as a reviewer. That you can log into that and submit your reviews, and our TA will check your review and grade you. So for paper reviews, so the deadline is actually soft. You have time until January 30, like end of January, to do the paper reviews. So you can actually update your reviews, add more reviews if you have time. So there is no really hard deadline for that. In the end, there is a hard deadline, but the hard deadline is not that close. But the second part of homework, which is about questions, like the exercise, those have a hard deadline. So like for homework, usually you have 2 weeks to do. And when the deadline is passed, basically you're not allowed to really resubmit. So there is a cutoff date for that part of homework that if you, unfortunately, you basically miss that cutoff, you're not able to deliver that homework. So make sure that you submit your solution to that homework earlier than cutoff, like the deadline. And the reason that there is a hard deadline is that immediately after the deadline, we're going to also release the solution of that homework. So it doesn't really make sense that you submit your solution after the deadline. So that's about for the homeworks. For labs, again, they have soft deadline because our goal is to, make you learn more. So we don't really want to, overwhelm you with all these hard deadlines. So there is a soft deadline for labs, which means that, but there is a basically bonus for students that they submit, deliver the labs by the soft deadline, which, for example, lab 1 is going to be in 3 weeks. So if you submit your labs in 3 weeks, like in 3 weeks or 2 weeks, depending on the deadline that we mentioned, TAs will review your labs after the deadline, after the soft deadline, and they will provide feedback to you. Like the feedback that how you can improve your lab. Or for example, if your lab has some correctness issue, they will also inform you. So you have this possibility that you work on your lab more and more and improve it and resubmit. That hopefully by the hard deadline, which is January, again, end of January, you're gonna get the full mark, for example, for that lab. So if you submit your lab before the soft deadline, you're gonna have feedback from the TAs. But if you miss that opportunity, you're not gonna have feedback from us. But if you have some questions about that lab or you want to get some feedback, you can still also attend our office hours, and then hopefully TAs will try to give you some answer about that. Is that clear? So all these things will be also clarified in the Moodle announcement that we share for Lab 1. Is it already released, Constantino? But yeah, it's going to be released soon. So our course website is on this link, which I think you already know. So all the slides, lecture videos, readings, assignments, they all will be posted there. And plus other useful information for the course. And please check frequently for announcements and due dates. This is homework 0, which is due by next week. So it's very simple. It's about, we want to have some information about you, like, which semester are you in, what are your interests. And all future grading is predicted on homework 0. So make sure that you submit homework 0 by this deadline. And these are some heads up that Lab 1 will be out soon, I think today. And it's going to do on October 11. Check the website and your email frequently for assignments and announcements. Homework 1 will be out on October 4th, and then it's going to do in 2 weeks after release. And our goal is to enable your learning and growth. So labs can be done anytime until the end of the semester. But as I said, if you want to have early feedback, you should submit before the soft deadline. So this is a required reading that we will also be part of homework 1, as I said, that you and your research, that we talked about it yesterday as well. You can read this again later if you want. These are also some suggested talk on mindset and research that I can basically direct you to from Professor Mutlu. Also, if you want to learn about Safari Research Group, like introduction of us and our research, you can check this talk in EFCL. And that brings me to the end of this lecture. Any questions? Any questions? Okay, then I hope you guys are gonna have a nice weekend and see you all next week.